Um, oh, oops. Do you see my slideshow?
Yeah, looks good. Do you have any videos or something
Oh,
that would?
I'll test soon. Do you see this video? Place where?
It's a little bit slow, but it looks okay. Yeah, I think it will
Yeah,
be
thank
okay.
you. Go. Yeah,
Okay.
I can start.
So maybe I can first share my screen and also introduce the you presenters today.
Oh,
And
yes.
Mhm.
Oh,
for the technicians here, could you also share the YouTube link? This session will be video streamed.
did you ask me?
No, no. The other
Oh,
technicians here. Hang or uh, I guess they are not hearing me. I guess we can just wait like one more minute.
yeah, yes, I can wait.
Yeah, I guess we can start now. So basically, this session will be also live streamed through the YouTube and also the Chinese platform, and the some audience will be attending this session through those kind of the other the platforms. And we're gonna also receive some kind of the questions from the audience from the other platforms as well. So we'll see how it goes. Um, Yeah, so let's get started. So welcome to the 37th session, the webinar session of the AsiaGraphics. I am Bin Sung from KAIST in South Korea. I will be chairing this session. So for this webinar, we're going to have the two very special speakers. The first speaker will be Shin-Young Lee from the Gyeonggi University in South Korea, and also the Quentin Becker, also from the University of Tokyo in Japan. And Shin Young is a assistant professor at the Gyeonggi University, and also he received his PhD from the KAIST in the computer science department. And his research lies at the intersection of the computer graphics, vision, and the computation of the imaging. We particularly focus on the physically based rendering and also some mathematical foundations of the graphics. And his recent work addresses many theoretical challenges in the representing the intensity of the polarized lights and in the also polarized light transport with the applications to the forward and the inverse rendering. So Xinjiang will talk about the high dimensional light transport and the theory and the applications. So please take it away. And also we're gonna have like 35 or 40 minutes of the presentations, and then we're gonna have some Q&A following that. Yeah. So please take it away.
Yep. Do you see my screen?
Yeah, looks good.
Yeah, let me start. Thank you for your introduction. Hello, everyone. I'm Shin Young-hee, an assistant professor at Kyung University in Korea. Today, I'd like to present my research interests, contributions, and future direction entitled Toward Higher Dimensional Light Transport. Let me briefly introduce myself. As already introduced by Minhyuk Sung, I received my PhD from KAIST Korea in February of last year, and after a 6-month postdoctoral period, I joined Kyunghee University as a faculty member. As many of you attending this webinar already know, rendering is a technique that computes images captured by a virtual sensor by simulating the propagation of light, its interaction with objects in a scene, Here, a scene is defined by several components: the geometry of objects, the material configuration of objects, especially some bidirectional reflectance distribution function, which determine light-matter interaction, and the distribution of light sources and how strong they are, and the sensor, usually camera configuration, and rendering is the process of computing images from this collection of scene information. And in addition to forward rendering, its inverse problem are also very important. Such inverse problem aims to recover scene properties such as geometry and materials from images captured by cameras. While this class of problems is also regarded as some topics in computer vision, these problems are also called inverse rendering by analogy to its forward counterpart. When we emphasize the physical relationship between a scene and captured images rather than computational methods, we often refer to this relationship as light transport. Such physical relationship is characterized by a governing equation named light transport equation, or also known as rendering equation. Traditionally, the primary physical quantity of this governing equation has been light intensity, more precisely radiance, which is a scalar valued function of position and direction. Here, the set of all position is 3D Euclidean space, and set of all directions is same as the set of all unit vectors, which is two-dimensional sphere. At this point, we can ask a natural question: is scalar intensity sufficient to describe all light phenomena or to capture all the information contained in a scene? Of course, scalar intensity is still widely useful in many scenarios, but there are phenomena that are better captured when we go beyond the scalar intensity. Beyond the scalar light transport model that considers scalar intensity as a function of position and direction, there exists many extended formulations of light transport that incorporate additional physical factors into light intensity. A major part of my research interest focuses on these physically extended versions of light transport. One example of this extension is transient light transport. When the light intensity emitted by a light source and the sensor's response vary over extremely short time scales on the order of nanoseconds to picoseconds, the measured images exhibit behavior like that shown in the right video, where strong pixel responses correspond only to light paths whose total length belongs to a specific temporal window. In transient light transport, the temporal physical quantity, time, must be account for the input value of light intensity. So we need one additional real number as its input. As we incorporate additional physical quantities, the dimensionalities of the domain or codomain of this physical quantity increases, which introduces new technique and conceptual challenges. This is why I refer to the title of this talk as higher dimensional light transport. So then why do we need this kind of a complicated formulation? The main reason to take care of these additional physical quantities is to obtain richer information from 3D scenes. In this perspective, transient light transport has several practical applications. First, non-line of sight imaging, for example, reconstructing hidden objects using 3 bounce light paths. In this case, 3 bounces of reflection discard most of scene information when we only use steady state, some conventional scalar images. So time-reserved images through transient light transport provide meaningful information for the hidden scene. And time of light depth imaging is another familiar case where images are weighted by light travel distance, making them a special form of transient imaging. Let me introduce another extension of scalar light transport. Note that light is physically characterized as electromagnetic waves in microscale. So we can consider light polarization for light transport. More concretely saying, when emitted light from light sources and reflected from objects is fully or partially polarized, And when images through a sensor system equipped with polarizing optical elements, the rendering and inverse rendering processes should be described using polarized light transport. In this case, light intensity is not a single scalar, but a set of four values known as the Stokes parameters. Light polarization also has wide applications, including diffuse specular separation, obtaining fine-scale surface normals, distinguishing objects that have almost the same scalar RGB colors, and measuring stress of some soft elastic objects. In the area of a higher dimensional light transport, which considers these diverse physical quantities, I have made contribution through three papers, one SIGGRAPH Asia paper on transient light transport and two SIGGRAPH and SIGGRAPH Asia papers on polarized light transport. Among the three papers, let me introduce the first one, entitled Differential Transient Rendering, which was presented at SIGGRAPH Asia 2021. However, as this paper was published about 5 years ago, so I will give a brief overview and mainly focus on its limitations and future directions. So the main motivation of this work is differential rendering, which is used to some entire inverse rendering pipeline. At the time, the 2021, no rendering algorithm existed that could provide accurate gradients for transient rendering with arbitrary n-bounce light paths. So we presented the first general-purpose differential transient rendering. So, and omitting some technical details due to limited time, I would like to introduce its application. As a first application, we try to solve inverse rendering problem of transparent objects. We are estimating several parameters of transparent objects, some rotation angle of red star and refractive index of blue star. After optimization steps, we observed that rotation angle can be converged with only using steady state image, but the BSDF difference of blue star between initial and target images are too small. So it would be better to see strict images which has X and T axis images. In this image, so the refractive index difference will be more visible. And next, we tried to track a hidden object around by not one corner, but two corners, which has not demonstrated. We are estimating a single coordinate of the position of the hidden object lies around two corners as the scene parameter. In XT strict image, we can see the optimized result is close to the target image. Now I'd like to discuss the limitations and future directions of this work. First, let me address its limitations as a differential ray tracing method, where I use the term differential ray tracing to mean the contribution of accurately computing the derivatives of rendered images themselves, rather than optimizing the full inverse rendering pipeline. First, while our work was the first one to provide an accurate, more precisely unbiased method for transient images, where the expected value of the resulting image converges to the ground truth differentiation. But it lacks acceleration techniques, or in Monte Carlo terms, it lacks some variance reduction techniques. As a result, this method is significantly slow. Whether handling differentiability or not, transient rendering itself involves some integrating a function with very sparse support, which makes acceleration method inherently difficult. Therefore, accelerating transient rendering remains a challenging and very exciting future direction. Next, I'd like to discuss a broader limitation of the differential ray tracing approach itself. Whether computing accurate gradients is truly the bottleneck of the full inverse rendering pipeline is an important question that has been actively discussed in the rendering community in recent years. So, and while these are not my contribution, I'd like to briefly introduce some related studies that I find inspiring and would like to build upon in future research. To address the limitation that differential ray tracing requires exact knowledge of all scene information, so several interesting approaches have been proposed. One direction is to represent intermediate optimization states using fuzzy representations such as NERF. Another approach is to model some components that have a small impact on the subject relative to the amount of information they require, such as near field illumination using NERF, while keeping the rest part explicitly. Yet another direction extends the definition of light transport by incorporating information about the uncertainty inherent in intermediate optimization states. I found these directions particularly exciting and hope to explore them in my own future work. Let me move on our work on polarized light transport. In the case of polarized light transport, we found a fundamental challenge that arises from the physical quantity itself used to describe the intensity of polarized light. Polarized light intensity is characterized as Stokes parameters rather than a single scalar. Here, Stokes parameters consist of four components for total intensity, linear polarization, and circular polarization. Here, these are very simple examples of Stokes parameter values of a single ray with total intensity 1. The first one is fully non-polarized light, and next four ones, for example, for linearly polarized light, and the other two for circularly polarized light. Here, the main challenge arises from the S1 and S2 Stokes parameters for linear polarization. Here we can observe that some 45-degree rotated rays has orthogonal numerical values in Stokes parameters, and 90-degree rotated rays has negated values in numerical values. It is very special properties in polarized light. So in summary, this property, this is a very special property of Stokes parameters. Note that Stokes parameters of a polarized ray can be measured under a reference frame. When we rotate the reference frame by theta, then the S1 and S2 linear polarization components rotate twice theta rather than theta. This twice rotation property enforces that we need each frame for each ray so that the z-axis must be aligned with the direction of propagation. There is no way to describe multiple rays within a single frame. For example, yeah, if we have two rays with different ray direction, we need to assign different local frames whose z-axis is aligned with ray propagation direction. So there is no way to measure these two rays in a single frame. So it raises some issue when we consider light intensity in directional domain. So consider that Stokes vectors on the directional domain are described as named some quantity named Stokes vector field, which can be considered as a polarized environment map. To measure it into four scalar fields for each Stokes parameters, we should assign a frame field defined on the sphere. Here, the problem is that the frame field contains a singularity which cannot be avoidable due to the Hare-Ribot theorem proven in differential geometry. So it raises the first fundamental challenge in some polarized light intensity. When a physical ray, shown in right, this black double-sided arrow, when a physical ray with a linearly polarized intensity moves continuously, it must yield discontinuous changes in numerical values in 4 components of Stokes parameters. Here, we highlight this challenge observed in Kim et al., a polarized extension of nerve. For certain camera poses, the output channels of S1 and S2 Stokes parameters exhibit a sign flipping artifact along a specific line. If we visualize ray direction corresponding to each pixel, because each image pixel is corresponding to ray direction, so ray direction can be visualized as a subset of some spherical domain. So we can see that the artifact consistently appears at a location corresponding to specific ray directions in the world frame. As a result, when the camera rotates, the artifact also rotates. When the camera is translated, the artifact remains stationary. And yeah, and this issue comes from that neural network only represent continuous functions of directions to Stokes parameters, but physical quantity of polarized light cannot be represented in some continuous values because this local frame singularity. So we need another representation of polarized light intensity rather than conventional Stokes parameters based on local frames. So the second challenge was identified from a different perspective. Rather than simply adapting some individual rendering method and individual inverse rendering method into polarized mode, we examined whether a more powerful tool, specifically spherical harmonics-based frequency domain methods, work well on polarized light transport or not. So why spherical harmonics work well and powerful in scalar intensity? It can be explained in terms of some useful properties such as rotation invariance and convolution. Spherical harmonics converge convolution into element-wise product. However, applying spherical harmonics directly into polarized light raise singularity issues because reference frames always contains its singularity. So applying spherical harmonics directly to polarized light do not hold rotation invariance and other useful properties. So we need a new kind of basis rather than conventional spherical harmonics for polarized light, which satisfy these kind of useful properties. And interestingly, we found the first challenge was more difficult and more some fundamental, and we success to address the second challenge first, and then found some way to apply the solution of challenge 2 to solve the challenge 1. So we will introduce our solution of challenge 2, which is presented at SIGGRAPH 2024. So, briefly summarizing our contribution, the main contribution of this work is to provide a frequency domain framework for polarized light, which generically extending conventional spherical harmonics framework. In our polarized spherical harmonic spaces, S0 and S3 components of Stokes vector field is expanded by conventional spherical harmonics, which is also called spin zero spherical harmonics, same as some existing methods. However, S1 and S2 Stokes components, which is for linear polarization, should be expanded with a novel basis named spin to spherical harmonics, like this shape. Then spin to spherical harmonics are continuously defined on the entire sphere without any singularity. Note that compared with the spin to spherical harmonics, the conventional ones are called spin zero spherical harmonics. And also, the spin to spherical harmonics bases were already invented in some physics field, so our work has contributions including both introducing existing theory developed in some mathematics or physics to graphics community, and our contribution also contains some new theoretical properties as well as providing real-time rendering application based on our theory. And briefly summarizing what is our theoretical contribution, it is well known that Fourier transform is very powerful and useful tools for various research fields. So, and the reason that the reason why Fourier transform is powerful can be summarized in terms of some operations like that. Translations of functions is converted into multiplying by scalar component in Fourier domain, where Fourier domain is same as directional domain, it's same as frequency domain, and some pointwise product is converted into convolution, and convolution into convolution is converted into pointwise product. As similar to this, it is known that spherical harmonics can provide some frequency domain framework on directional scalar valued directional domain functions in terms of this kind of operations. And also spherical harmonics is also existing and well-known theory. And our contribution is that our polarized spherical harmonics provides frequency domain framework for Stokes vector valued directional domain functions. In other words, polarized intensity valued directional domain functions. And in terms of such operations, rotation, rendering equation, visibility mask, which is pointwise product, and convolution, and some operations, there are some existing theorem proven in mathematics and physics, but some other operations, we also provided some new theorem which has not been proven in other fields. And our theory was constructed through carefully step-by-step derivations. Due to the time limit, we cannot cover all the derivations, but please refer to our paper. And as application, adapting existing pre-computed radiance transfer pipeline by equipping our polarized spherical harmonics theory, we also provide real-time polarized rendering, which taking polarized environment light and pre-computed shadow into account. Our polarized rendering method is also capable to real-time adjustment of linear in this video. In this video, this UI indicates the direction of linear polarizing filter equipped by the camera sensor. And next, let me introduce our last work, which is presented at SIGGRAPH Asia 2025, which is addressing the challenge about discontinuity of Stokes parameters in directional domain. First, let me briefly introduce the core idea to provide new parameterization of polarized intensity. And as a result of the previous work, which is presented at SIGGRAPH 2024, spin to spherical harmonics is known to provide some continuous basis for entire directional domain. So spin to spherical harmonics allow an arbitrary Stokes vector field, which is defined on entire directional domain, to be expressed as a linear combination of basis functions and coefficients. However, this representation only provides a frequency-limited lossy information and also has not been used to represent a single ray, not single ray, but some entire distribution on directional domain. But our key idea is to reinterpret a single ray single ray Stokes vector. So single ray polarized ray as Stokes vector field. So single ray as direct delta field. And by taking only the minimal frequency level of coefficients, namely order L is equal to coefficients, these 10 coefficients finally return into our new frame-free representation named S2L2 representation. Note that such 10 parameters cannot exactly reconstruct general Stokes vector field, but under the direct delta constraint, the original single Stokes vector can be exactly reconstructed. Here, also note that our S2L2 representation named after spin 2 and L is equal to, and it satisfies several useful properties, some named invertible and linear, and providing a rotation invariant metric. Please refer to our statements and proofs please refer to our paper for our statements and proofs. And first, our results, we demonstrate the one parameter motion of physical polarized ray. At the right side, we now provide a continuous value change of when the physical ray moves continuously, compared with the conventional frame-dependent representation yield some discontinuous value changes. We also found that these singularity issues arise even in more simpler application. An environment map can be represented in various formats, such as cube maps, equirectangular maps, or perspective images. And convergence between these representations involve resampling across different spherical pixel grids implemented via bilinear interpolation. Why this is a relatively straightforward task for unpolarized intensity, but performing the same operation using frame field-based Stokes parameters, some conventional representation, it leads to large interpolation errors when pixels straddle a frame field singularity. In contrast, when we replace this with interpolation in our S2L2 parameter images, these singularity artifacts disappear. We also demonstrate an application to polarized radiance field. Here, we examine Kim's method under different world coordinate configuration. When the world coordinate system is rotated so that the camera field of view includes a frame field singularity, we observe a sign flipping artifact at locations of specific ray directions in each world coordinate system. This is because the neural network outputs Stokes parameters defined under a specific frame field. When we replace this neural net output with our S2L2 representation, the singularity problem is resolved. Yeah. And simply summarizing some take-home message of our two papers of polarized transport. If you want to extend existing spherical harmonics-based methods into polarized versions, our SIGGRAPH 2024 paper would be helpful. And if you want to make your neural net representation, the neural net represent a function from directions to polarized light intensity, our SIGGRAPH Asia 2025 paper would be helpful. And as a limitation of this work, currently we need 12 parameters to represent 4 Stokes parameters. So 12 is so high dimensional. So finding a fewer parameterization would be very interesting future work. So now I'd like to introduce my future direction. To summarize, my previous work has focused on higher dimensional light transport, including spectral light transport, which I did not introduce here, but it is explored in a project where I contributed as a co-author, and as well as transient and polarized light transport. A key point is that when these extended physical properties are taken into account, the captured images contain much richer information about the underlying scene. Building on these experiences, I see several future directions. First, I'm interested in physical extensions I have not yet explored, such as wave optics light transport, involving some optical coherence or diffraction. And second, while my previous work were more focused on some theoretical work, but I would like to tackle more practical inverse problems that exploit the rich information encoded in higher dimensional measurements. Finally, I believe these rich simulations accounting for rich physical properties can contribute not only to graphics, but also to scientifically reliable scene understanding, for example, through collaborations with some other scientific research field, for example, remote sensing. And thank you for listening. If you have any question, it will be welcome. Yeah, thank you for listening.
Okay, yeah, thank you for the great talk. It was really insightful talk that describes many kind of the interesting the ideas about the polarized light transport. For the technicians here, if you see any questions on the other platforms, please post the questions in the Zoom chat so we can basically follow up with all the questions. So while we wait for some questions from the audience, I'd like to ask some questions. Obviously, I'm not the expert in this field, so my question might be about some very basic things, about some dumb questions. But one question that I had is that for the third the paper that you're presenting, so my understanding is that these are like all the idea about like performing some kind of the Fourier transform, basically analyzing the free and field the information in the frequency domain.
Yeah.
And you mentioned that you basically cut the basis function to the level 2. So that sounds like there is some kind of the assumption that the frame field over the sphere might be some kind of the smooth the function. So actually, I was wondering, so typically how smooth the frame field the information, and would there be any kind of the cases
Ah,
that we need to somehow handle some high frequency the information?
so maybe this idea will be some tricky for listeners. So this is idea, but yeah. The basis function is originally designed to approximate some entire distribution, but here in this problem, we are only interested in a single ray. So, yeah, if if we only want to recover a single ray, saying this direction, saying this position on the sphere, so even if another position the function has been smoothed, but some directional polarization at this point is preserved, and the amount of some original direct delta intensity with multiplied by some constant less than 1, but such constant is very constant, such exactly square root of 4 pi over 5. So we can exactly recover. So I can provide some analogy. If we are trying to represent a single tangent vector on the sphere, then we already know some common solution. Then for tangent vectors, we can use some one single global frame to represent this tangent vector and this tangent vector. But this way is equivalent to if we can get some conventional spherical harmonics coefficient for some tangent vectors xyz coordinate, then yeah, some real spherical harmonics of order 1 is equivalent to x comma y comma z. So it is hard to explain, but
I see.
Yeah, yeah. In summary, it is idea, some tricky idea, but it is not approximation.
Oh, I see. I see. So
Yeah.
actually, these bases are sufficient to basically represent the playing field in the case, like when you specify the instruction.
Yeah, yeah, yeah. So that can be more intuitive in this video. Previously, we need this frame and four parameters, and now we do not need any frame, and these 20 parameter exactly represent this polarized ray.
Yeah, this sounds quite interesting. Um, Actually, also one more the question
Yeah,
regarding the frequency domain, the analysis of the
yeah,
different field was that so
yeah,
probably maybe I missed, but you
yeah,
mentioned that those kind of some frequency domain the analysis also
yeah.
helps the real time the rendering of the polarized lighting.
Ah,
So
yeah,
I
yeah.
couldn't
I
see
I
the connection
omitted.
between these two.
Yeah, I omitted. So there are some real-time non-polarized rendering framework named Pre-Computed Radiance Transfer, which is developed some 2002, and it is famous in some rendering researchers. So it converts some, yeah, rendering equations is some integration in sphere, so it can be converted in spherical harmonics domain. It can be converted in some matrix vector multiplication, and pre-computed radiance transfer is highly based on such spherical harmonics frequency domain operations. So we just substitute existing spherical harmonics operation into polarized spherical harmonics operations. So adapting this application method was relatively straightforward.
I see. So some
Yeah,
kind of the matrix multiplication
yeah,
becomes
yeah,
like elemental-wise multiplication in the
yeah, yeah,
frequency
yeah,
domain, and
yeah,
that helps.
yeah, yeah, yeah. This was matrix multiplication, and this was some frequency domain convolution. Yeah, yeah. These or all these four kind of operations are used in this real-time polarized rendering pipeline.
That's quick question is that for the conversion to the
Yeah.
spectral domain and the spatial domain, do you use some kind of the pre-implemented the Fourier transform the some API or some library where did you
Oh.
implement like all those things yourself?
Yeah. Ah.
Because like in the Python or whatever some kind of the for the libraries basically there will be some kind of the pre-implemented some kind of the
Yeah.
Fourier transform the fast
In
Fourier transform the functions, right? So
Yeah,
is that you use
so
those kind of things or
in this SIGGRAPH 2024 papers, our implementation is split in some Python. We both implemented in Python and some C++. So to check some our theory work well, I build some Python implementation, but I use some Python scientific library, which is implemented in some physics field to for this spin to spherical harmonics implementation. But in C++ implementation, I was right. I wrote the yeah, yeah. I used existing conventional SH-based rendering C++ implementation, I added some Spin 2 version. So yeah, yeah. In implementation, I also tried many some
I see.
dirty equation into code.
I see.
Yeah.
Yeah, I guess that there might be some lots of some kind of the engineering efforts as well in terms of achieving those kind
Yeah, 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 yeah. Yeah, that was not small.
One quick the last question that I had is that
Yeah,
so for those kind of the some the parameterization of the polarized
yeah.
the lighting, you mentioned at the beginning that you basically introduce like for the types of the some strokes the vectors and everything is basically represented as kind of some linear combinations like for those like four
This
types
one?
of the uh yeah probably yeah this one yeah so you have like
Yeah,
it's
yeah.
kind of like you have the four types of some specific some polarization decrease to my understanding, and representing everything is
Yeah.
kind of a linear combination of that. So actually, I was wondering how good this kind of the model is. Like, can this kind of the representation
Yes,
really
yes.
represent like
Yeah,
all
yeah.
possible physical properties or not?
Yeah, so since this slide is very beginning slide, so I was more focused I was more focused on providing some motivation of some physical quantity polarization. But this codomain alpha notation is completely don't match to the challenges introduced in later parts. Yeah.
But I
Yeah.
can say that it's kind of the
Yeah.
convention to have those kind of the four the types and representing everything
Yeah.
is kind of linear combination of that. But I was wondering whether this is
Yeah.
the perfect model where this is kind of the good approximation, but there might be some
Ah,
real like
so
more
so
complex
it yeah, yeah.
cases, real difficult.
Yeah, yeah. It depends on which properties we want to make hold. So if we are only interested in linearity, then this formulation preserves linearity, but continuity is not preserved in this formulation.
That's that's also something.
Yeah, yeah. Continuity and yeah, some in my slides. Yeah, when we apply conventional spherical harmonics with frame field for polarized light, linearity is also preserved, but some rotation invariance and continuity and convolution are not preserved. So it depends on which properties we are interested in.
Hmm. Yeah, thank you for the great talk. If there is no other questions from the audience. Yeah, I guess then we can move on to the second talk. So yeah, thank you, Shinyo, for the great talk.
Thank you.
Will you share my screen again?
Yes.
Yeah, so as the second speaker, we're gonna have Quentin Becker, who is the postdoctoral researcher in the computer science at the University of Tokyo, as part of both the user interface research group led by the Takeo Igarashi, and also the Taichi lab by the Tomohiro Taichi. And he received his PhD in the computer science from the EPFL under the supervision of the Mark Pauly, where he developed the algorithm to simulate, explore, optimize, and also rationalize the deployable grid shells with the curved elastic beams. And during his PhDs, he also interned at the Google Research, where he worked on the geometry simplification through the geometric primitive decomposition. And his research focuses on the efficiently solving some inverse problems related to geometry and also the physics by designing some suitable regularizations, relaxations, and also the subspace representations. So today, Quentin will talk about the geometry-informed inverse design for the architecture and the robotics. Yeah, so please. Yeah.
All right. Thanks a lot for the introduction. Can you see my screen?
Yes.
Okay, all good. Yeah, thanks for the introduction. So I'm very happy to be here and present my work. Today, I would like to actually add from architecture and robotics, I would like to add animation as well. But first, let me give you a piece of introduction about myself. So we are going to talk about all of these things moving on the screen soon. So I'm Quentin, currently a postdoc at Igarashi Laboratory and Tachi Laboratory. And prior to joining these laboratories, I had the chance to travel around for my studies. So from France to study aeronautical and aerospace engineering, to Berkeley in mechanical engineering, and finally Lausanne at EPFL to study physical simulation and computational design. In particular, I'm fascinated by the use of geometry to simplify ill-posed problems related to physics. During my PhD, I worked on simulating and optimizing seashells, flexible deployable grids, then finding ways to build them from a sparse kit of parts. I also studied and described tubular surfaces that could be made out of glued paper with applications in furniture design and architecture. and recently on temporal control problems for shape-changing bodies. We'll talk about the way this stingray learned to flap its fins later. So, and I hope that you will see how these topics are connected through the lens of geometry and physics. So let's start by defining some terms. Control variables such as motors, rest shapes, etc. are parameters that drive the evolution of a physical system. Solving the forward problem allows describing the state of the system after letting it interact with its environment. It is often well posed. That is, there is a unique observed state stemming from a set of control variables. More challenging is solving the inverse problem. That is, answering what set of parameters should I pick in order to observe a given state. Similar to what we saw with inverse rendering, it is ill-posed. So there could be many or no solution at all. Inverse problems can be found across many domains. So here I focus on physics-based animation, where, for example, this ancient creature needs to be realistically animated, so it appears like swimming. And previous work from Huang and colleagues tackles the inverse problem in differentiable framework where friction contacts are accounted for. Robots need to be actuated in the right way to achieve the desired motion and reach a target. We can see a salamander from the biorobotics laboratory transitioning between two media, and a swimming jellyfish-inspired robot from Run and colleagues. Kinematic deployment of architectural structures, such as the asymptotic grid shells from Shikore and coworkers, also require great care for the deployed state to approximate its intended shape. To solve such inverse problems, let's go back to that picture. It is common to introduce a notion of objective and measure how well the observed state complies with our constraints. We can cast inverse design as a minimization problem with the constraint that the objective is physically derived from the control variables. This pattern is actually common across my projects. However, directly solving the optimization problem using continuous optimization rarely succeeds due to the highly non-convex nature of the forward simulation or combinatorial nature. Initializing the control variables correctly is therefore mandatory. This is probably the most important part. So finding a good geometric abstraction not only effectively allows you to serve this purpose, but it also builds intuition and brings new insights on the phenomena at stake. So I would like to give you a concrete example next, but I will first have to define what I mean by grid shells. So that's my PhD work. And this would not have been possible without the help of these people. So Saichi, Udai, Samara, Florian, Julian, and Mark. Let's first define what a grid shell is. So grid shells were also referred to as lattice shells at the beginning, and they were defined as doubly curved surface formed from a lattice of timber lath bolted together at uniform space in two directions. So let's see what it means. It describes the manufacturing of the multi-halle in Mannheim, which is this gigantic grid shell designed by Professor Frei Otto and Ovi Harrop and partners. It spans about 10,000 meters square and is 20 meters high. So it's huge. You can see two more recent monumental grid shell structures designed by Buro Happold. So the Wild and Donland grid shell building and the Savile building in the UK. Timber is brought by trucks in their straight configurations, allowing for easy transportation. Construction is done in place, and the erection of the grid requires great care and coordination. Deployable grid shells can be easily assembled in a low energy state, so not in place, and deployed into a 3D shape, such as for the this X-shell pavilion. Elastic geodesic grids further ensure zero energy assembly states by introducing sliding notches at the joints. So the X-shells might not have a zero energy rest state. Our C-shells enable irregular grids like X-shells, but use curved beams as a primitive, effectively allowing the assembly state to be stress-free using rotational joints only. So let's see, and take this curved elastic beam. If we pull from one end, we increase the elastic energy of the system, and then it relaxes to its original state. The beams are laid out in a plane and attached through single-axis rotational joints. Through actuation, the C-shell achieves its intended shape. Okay, so before presenting the computational design framework developed around seashells, I would like to bring some geometric intuition about the deployment of elastic grid shell. Not physical exactly. It's physical motivated, but eventually we just abstract it with geometry. So let's start from a single straight elastic rod. We assume its cross-section to have a stiffer direction, so that's the physics part of it. And if we keep one end fixed and pull on the other ends, you see that the rod pops out of plane and prefers bending along the weak axis. Let's combine some rods using rotational joints. The beams can only rotate about one axis with respect to each other. And if we pull the linkage, the structure will simply shear, and it's a rigid mechanism, so nothing happens. Take the same grid shell, but make this shearing motion rigidly infeasible by changing the positioning of one beam. Now the linkage prefers to buckle out of plane and deforms. The question we want to answer now, can we make sense of that geometrically? Can we predict other interesting behavior from this abstraction? So we start from the flat state and consider a surface of a fictitious membrane attached to it. It has a surface M and a boundary del M. We can also name the inner angles of the quadrilateral with beta. All these quantities are related with the Gauss-Bonnet theorem, which in simple terms says that the Gaussian curvature of the surface plus the geodesic curvature of the boundary minus the sum of inner angles is constant. But we know that ribbons don't bend in plane. That's what we saw at the beginning. So we are left with two terms. Note that you find that the sum of the angles of a planar quadrilateral sums to 2 pi. So that's a generalization of this fact. Now we imagine that we can force the angles to be whatever with some small motors. If we decrease the sum of inner angles, the total Gaussian curvature must also decrease, and it becomes negative. So it is a saddle. That's what we saw before, but explained in geometric terms now. So we decreased the sum of inner angles, but we could have increased it. And we know that in that case, the surface curvature must also increase. The surface becomes spherical or dome-like, so positively curved. So how do we get these shapes? The answer is that you ask Saichi Suzuki, a postdoc in my former laboratory at EPFL, but there has to be a better solution. So he designed all of these. You can see that we can achieve different topologies, and seashells can approximate a wide variety of shapes. These are quite wide. Let's see how we can generate and simulate such designs. So curves in the linkage are parameterized using interpolating cubic splines. They have to go through joints. Joints and additional control points serve to parameterize them. You can note how when I vary the control points, the whole linkage topology is preserved, so the way the beams are connected. Equilibrium states of a system are minimizers of the physical system's energy. These structures behave like springs. They have a rest state, and any deformation costs some energy, measured with the discrete elastic rods model from Bergou and colleagues. Our seashells are energy-free in their assembly states by construction. So here, if we minimize it, nothing happens. We simulate deployment by solving a series of constraint minimization problems using Newton's methods and exploiting the sparsity pattern of the energization for efficiency. Our structures can be actuated in various ways, so torque actuation at the joint pinning, and string actuation. Here, we may control the actuation extent by uniform torque tau at the joints. Increasing that value deploys the linkage to its final shape. And you see that it is nearly a 1DOF system. So let's now see how to get nice splines for those seashells. So we formulate the design exploration process as an edit to an initial linkage. We look for smooth functions that preserve the deployability of a linkage. A subset of such edits are conformal maps which are smooth and preserve angles. Our paper at ISS details why and present two intuitive ways to manipulate such maps. So Mobius transformations project the linkage on a sphere. The sphere can be rotated and the linkage is projected back to the plane. Alternatively, tools such as boundary first flattening or BFF allows the user to manipulate a boundary and automatically propagates edit in the domain in an angle preserving fashion. Those designs were obtained using our Grasshopper plugin from various topologies and deploy into these interesting shapes. We now propose a computational pipeline to solve the inverse problem. Here is an overview. We start from a target surface represented as a surface patch. Our computational design component optimizes the beam given a grid topology, that is the way rods are connected, and the deployed state must approximate the target surface. We finally fabricate the optimized prototypes to validate our methods. We now look into the different components constituting the computational design block. Our planarization algorithm finds a candidate seashell that deploys into that surface, and the initial guess is then refined towards the input surface through our design optimization algorithm. Let's start with the planarization algorithm. So you take this surface patch we want to approximate and trace curves on the target surface following UV isolines to produce a reference deployed state. We also initialize a flat state and now have this reference flat state and reference deployed states. But as if you remember, the flat state is likely not to deploy at all. It's like the example at the beginning. We then optimize the joint positions in the flat state along with the joints on the target surface. And our objective makes sure the two states match here by ensuring that the beams have the same length between two joints. And if we run it, you see that the joints move together and the mismatch is reduced. Once initial design has been found, we use our design optimization algorithm to refine it. The initial seashell may have high stresses in its deployed state. Additionally, it may poorly approximate the target surface, here a torus cut in half. We update the curves in the flat layouts and the torque actuation as well in a fully differentiable pipeline. The total objective is composed of two terms, so target fitting, which measures the distance of each joint to its projection on the target mesh, and the elastic energy in the deployed state, which are minimized. We optimize the beam shapes using first-order sensitivity analysis, so on the left-hand side. So I will now take a small detour and show you an interesting fact. Let's take this optimized layout and try to redeploy it. You see that it finds a lower energy deployed state, which is interesting. Let's try a different deployment technique. We first hold the joints in the inner and outer rings and release them. We recover our original shape. So you see also that applying opposite torque gives a negatively curved shape as predicted again by Gauss-Bonnet, something we saw at the beginning. So can we exploit the isometries of a deployed state to detect other stable states and have multi-stability? Back to our pipeline. These components form the computational design part, and we fabricate prototypes to validate the methods. The fabrication process is in 3 steps. So the beams are laser cut from flat sheets of material. They are laid out, and the holes are aligned to welcome screws that serve as single axis joints. Notice that the beams need not to be deformed in the deployed state. The holes perfectly align. And third, the prototype is deployed by hand, and the screws can be tightened to hold it in place. Here is a prototype made of acrylic, which is quite brittle. We scanned the models to compare our simulation against the fabricated prototypes, showing good agreement. Let's make seashells from repetitive elements instead of those bespoke curved beams. So we start from this seashell design. Let's see what I mean here with this one. So you take the flat assembly states and take the curved beams apart. You see that there is potential material waste due to improper packing, and these elements can hardly be recombined for other structures. Zoom tools, on the other hand, are commercially available sticks and spherical joints that can be assembled to get complex and interesting structures. In an architectural context, Boeting and colleagues use and optimize this set of parts to achieve different assemblies. Such a kit-of-part approach enables sharing parts across models while being scalable and stress efficient. So can we apply the same principle to find a small set of parts that can be combined while preserving the original deployed state? And more broadly, can we apply our methods to multiple designs at once? I'll try to give an overview of some technical parts from our paper. Our solution starts from a discretization of the original designs, from curved to piecewise straight beams. The computational framework consists of a two-stage rationalization algorithm. We recover the assignments and a kit of parts across the original designs. We briefly show what a discretized C-shell is. So start from our design, place one beam, and discretize it using a polyline that interpolates the joints. The continuous curve is now a rigid polyline. More precisely, given the rotational joints and an initial direction and a length, we can trace a first straight element. Since the polyline must interpolate joints, the next direction and length LC2 are prescribed. We can still choose LC3 freely. We connect the element using a rigid joint and repeat the operation until we've traced the whole curve. Note that the first and last elements are cut in half. So our rest variables are given by the segment length and turning angles. We allow for non-stress-free rest configurations, similar to X-shells. But as we discretize it, the state starts with a stress-free assembly state. So as previously, we can apply uniform torque at the joints and deploy the linkage. Okay, so now let's describe how part assignments are done. We take a straight element from this discretized C-shell and plot it in this diagram as a 2D points. Points on the axis are split elements. They are located at the start and end of the curves. We define special elements termed parts and assign them according to a distance function. Since each part can be used in its flip configuration, we represent them on the top left part of the space. There is a symmetry. We have defined parts Pi, elements Qj, which are instances of their closest parts, and distances with ρ. The parts update consists of in an expectation maximization algorithm similar to k-means, which you might be familiar with. Assignments and parts are updated at each step until convergence. Okay, so from elements Qj, we may recover the parts shape Pi and assignments Cj. We define a projection energy as the inertia of the assignments with some element to parts distances. It represents how well the elements can be clustered. Going back to our problem, and let's increase the number of parts to 8. We can project elements to parts directly and run equilibrium, and you see that it gets into this buckled state that we can deploy again, but it painfully does it. So can we do better than that? And our rationalization pipeline jointly improves the parts shapes and their assignments on the linkage through continuous optimization. Let's take this example and add some more designs, because that's what we wanted to do at the beginning. Rationalization consists in finding the best parts P and assignments C according to the preservation metric, the sum of target fitting and energy in the deployed states, similar to the design optimization for C-shells that we saw before. However, the number of parts is exponential in the number of elements. So this huge number makes exhaustive search intractable in practice. We can try to fix the original assignments found using our methods and only optimize the parts. So before we only fixed the parts to what they were. Now we try to also optimize their shapes. If we do that, you see that the design suffered a bit and the flat and deployed state are severely buckled due to geometric incompatibilities. So let's start over. And before projecting elements to parts, we we keep them as they are, we keep elements, but try to get them as close as possible to the to the parts. So we add this projection energy, this grouping energy. And if we do that, we obtain much nicer results on the same shape set of designs. Although you can see that we can hardly preserve a flat rest state in this context, but this is a clear improvement. Note that our method can be is more broadly applicable to other bending active systems, such as umbrella meshes here, or on static grid shells with orthogonally oriented lamellas. So combining instances from this kit of parts here allows constructing these 10 designs. So I told you about this swimming stingray. I would now like to talk about one of my most recent works, inverse geometric locomotion, presented last year at AsiaGraph. So the connection that I can make and that you will see relates this work is that we replace a costly CFD simulator with a cheap but accurate and robust fluid simulator that relies on geometric invariance. So here, geometry is crucial in order to make some problems that were intractable before computationally feasible nowadays. So geometry is the key to that. So it is a joint work with Oliver Gross and my former advisor, Mark Parley. I start by pointing out the diversity of modes of locomotion found in nature. Astronauts, divers, and cats have learned to rotate to achieve a task or to mitigate damages caused by a fall. And bacteria, worms, and snakes slither to efficiently navigate in damped media. They all fall in the category of geometric locomotion, that is, scenarios where the motion is completely determined from shape changes. For now, we'll focus on the slithering locomotion of snakes. When a snake changes its body shape, its scales interact with the environment and propel the snake forwards. So it is natural to ask to identify the shape sequence that achieves some prescribed displacements. Take this snake, for example. It has to translate from point A to B. One can probably come up with a solution and manually design periodic undulations to exactly reach the targets. Now, adding two obstacles and further asking the snake to visit checkpoints in between makes this work extremely tedious for an animator. With our methods, we can identify a number of solutions in a matter of minutes on a laptop. Moreover, it provides enough flexibility to account for a variety of criteria for the gates, be it to reach a target, avoid obstacles, or efficiency. The main challenge when facing these space-time optimization problems is a trade-off between physical accuracy and computational complexity due to a typically high dimensionality. Space-time interpolations simplify the problem at the expense of violating the equations of motion away from some control points. Some geometric formulations overcome this difficulty and allow physically sound interpolation, but they do not scale well, rendering them impractical for animation tasks where long sequences of high-resolution meshes are manipulated. So with our methods, we reconcile both, providing a flexible and realistic method for animators based on a novel approach to the geometric problem formulation. So I'll start by briefly introducing concepts to describe locomotion in abstract geometric terms, which leads to a structure-preserving forward integrator. Then we derive an efficient inverse design algorithm to identify shape sequences that achieve user-defined tasks. Finally, we show a number of strategies to reduce the dimensionality in time and space. Let's dive in and see how we think about locomotion, carefully distinguishing between shapes and their positions. Okay, so this is a snake. Its pose corresponds to one point in the shape space. Moving the point in the shape space, we see the different shapes. When positioning the shape in the world space, we also specify an orientation and a translation, that is a rigid transformation. We associate the collection of all of its possible positions to the shape. This fiber is essentially the group of rigid body transformations. Moving along this fiber, we position the snake in the world space, keeping its original pose intact. Since we can do so for any shape, The space of all position shapes has the structure of a fiber bundle. A shape sequence, or gate, is a curve in the shape space, specifying a shape for each point of a time interval. Motion trajectories are curves in the positioned shape space, traversing the corresponding fibers. They need not carry any physical meaning. Taking a Lagrangian point of view, physical motion trajectories can be determined by means of variational principles, namely Helmholtz's principle of least dissipation. Variational indicates that they are a stationary point of an energy, which depends on the choice of a Riemannian metric. This metric allows us to measure length and angles on the positioned shape space. Typical choices model energy dissipation due to friction in dissipation-dominated scenarios, or in inertia-dominated scenarios, one can model the kinetic energy of the system. We can position the shapes in a sequence in a number of different ways. It turns out, to do so physically, we can follow a simple rule. Starting from any position shape, we position the next shape by traversing the corresponding fiber orthogonally, or in other words, horizontally. So with the forward simulation in place, we can now go on to the inverse problem. The kind of inverse problems we are interested in involve motion planning and optimization. This can be cast as an optimization problem where objectives enforcing multiple tasks are gathered into a single objective function that depends on the motion trajectory. The shape sequence alone is our optimization variable, since it implicitly defines the motion trajectory. The motion trajectory must be physical at any step of the optimization, hence horizontal. And last, the motion trajectory and the motion sequence should be compatible, which our implicit definition ensures by construction. Okay. So we solve this minimization problem using continuous optimization. Okay, so crucially, we need to think about how an objective, here reaching a target, changes as we perturb the gates. That is, we need to compute the gradients of the objective seen as a function of the shape sequence. The physicality or horizontality constraint implicitly relates the gate, the shape sequence, to the motion trajectory. Using the adjoint method, we find an explicit recursion, which allows us to backpropagate in time this sensitivity from one time step to the previous at the expense of solving a 6x6 linear system. We feed these gradients to an off-the-shelf optimization algorithm and let it teach a snake to turn 180 degrees in this square box. And we recover a characteristic turning behavior that can be observed in nature. In general, such inverse problems are ill-posed and have either no solution or lots of undesired solutions. Our setup allows reducing dimensions and biasing gates towards smooth and energy-efficient shape sequences. Continuous shape sequence is a succession of shapes and therefore lives in a continuous space along the time axis. Since finding the minimizer of the previous inverse design problem is often intractable in this space, we define a handful of control points, which serve as optimization variables, and use them as interpolation points for a QX spline, which represents our continuous gate, the shape sequence. In opposition to existing collocation methods, our approach ensures that the discrete equations of motion are exactly satisfied. We successively interpolate control points, discretize the spline, and forward integrate the trajectory. The resulting optimal motion trajectory is then physical by construction. So let's take this disk and ask it to translate to the right one diameter. We see it manages to reach the target, but deforms unrealistically, and that's normal. We haven't prescribed anything. Our method offers a flexible design framework incorporating a variety of regularizations we can explore, influence, and craft shape sequences. To reduce the spatial dimensions of the inverse problems, we may restrict the shapes to subspaces defined by a lower dimensional parameter space and smoothly map it to the full shape space. Our design variables now live directly in the parameter space. So take this sphere to translate to the right. On the left, We optimize all vertex positions together with the same isometry regularizations as for the disk. We use lower dimensional linear subspaces for the two spheres on the right and get these very different gates. Combining both reduced shape spaces and shape interpolations, we can design and solve complex motion planning tasks, such as the swimming motion of this stingray, undulating its spectral fins. This is purely from geometric principles. We start from random noise at the beginning. Okay, more technical details on the forward simulation can be found in Motion from Shape Change from Gross and colleague, and our paper Inverse Geometric Locomotion for the inverse design part. Let's showcase the versatility of our approach across different examples. We start by dropping a cat and expecting it to land on its paws. I'm not sure I've ever observed such a technique, but let me assure you that the equations of motion are satisfied exactly. So our method allows for users to add semantics and guide the solution towards a more realistic sequence. Now, consider these snake robots composed of motorized hinges. Goal is to reach the checkerboard flag. Our algorithm successfully finds gates that achieve this task with and without dissipated energy regularization. Even in case of hinge failure, our method recovers a valid and energy-efficient gate that achieves the task. In an ongoing project, we study how well our method describes the motion of a robot snake mounted on wheels. One key point we address here is detecting which actuators are the most essential to preserve efficient locomotion and shelter them from breakage. Now, consider this abstract locomotor, which can flap its three wings about the central triangle. While it would be unintuitive, at least for me, how to flap wings and realize prescribed motions, our method easily finds ways to translate, rotate in plane, and out of plane. Going beyond the control problem, can we determine what the optimal flapping robot should look like? How many hinges does it need? So looking ahead for future work, soft robots offload control onto the morphology of the body itself, achieving complex motion with fewer actuated degrees of freedom. This requires robust simulation tools, motivating our variational approach. Consider this 1DOF fish. Our current framework captures body fluid coupling, but neglects fin compliance. We aim to extend it to compliant shape, redefining physical trajectories accordingly. In the current work with Clément, Oliver, and Sina, we explore ways to efficiently simulate and control immersed soft bodies. And as this symmetric swimmer suggests, it is probably possible. Lastly, so C-tubes is a class of stiff tubular structures made of flat ribbons glued together and were introduced during SIGGRAPH. They show a way to enforce fabrication constraints directly in the geometry. So again, we abstract the fabrication constraint into geometric concepts that can be easily integrated in the design process. It's a joint work with Michele, Clara, Florian, and Marc. Let me start with a preview of what a C-tube is. Here, you're seeing an optimized 2D strip layout copied using our algorithm. And if we cut and assemble these strips, for example, from a sheet of paper, we get a stiff, hollowed 3D structure. Here, you see an example of a prototype we fabricated by laser cutting the strips from a sheet of plastic material and added a neon tube inside to make a line. C-tubes span a large variety of shapes, yet they are easily manufacturable and structurally performed. In this work, we focus on cone nets that have closed polygon as a generatrix curve. In this case, each edge of this polygon sweeps a separate strip. If the directrix curve or directrix is a smooth curve, we get a semi-discrete surface with smooth strips. If the directrix is a polyline, we get a discrete surface where each strip is made by construction only of planar quads. This is a key property. Building upon these insights, we propose an efficient parameterization of tubular cone nets, cone tubes, or C-tubes for short. Besides the directrix and cross-section, we control the orientation of the sectioning planes via their normal P and the shape of the tangent cones by the location of their apices. To encode the cone apices, we use a single scalar value per cone, which we collectively call apex locating function. C-tubes are hollowed, and this allows using them as formwork for freeform casting, like in this lighting fixture. The ease of fabrication of the strips could dramatically cut costs compared to 3D printed or milled custom molds. Let's go back to the lamp we've seen in the beginning, and note that simply sweeping the directrix will not, in general, close up smoothly. To make the tube ends match, we modify the directrix. You can see how the strips change shape. If we introduce additional constraints, for example, that each individual strip closes up on itself, the deviation from the intended design can increase substantially. More details on how we mitigate this deviation by introducing more optimization variables can be found in the paper. So around Tokyo, I found this suspension bridge. This is a C-tube, and it has probably been optimized to bear the loads prescribed by the cables connected to the bridge. I was wondering, how can we then include stiffness maximization given certain load scenario in the optimization? This seems to have concrete applications already. And in a publication to AAG, we recently proposed design strategies for cone nets, which are T-tubes with open profiles. So you can design your own now. Let me now wrap up. We presented this inverse design pipeline and advocated for the need of a good geometric abstraction. I hope that you are now convinced of the efficiency of such a methodology when it comes to tackling highly challenging inverse problems. So be it on initializing the solution for further optimization, or by changing the simulation itself using geometric abstractions. So that's what we've shown, or even incorporating fabrication constraints through geometric quantities. So I'm mainly interested in three directions across these topics. So first, topology and morphology exploration are inherently discrete. So can we reduce combinatorics through clever relaxations to make this problem tractable? Second, accuracy and efficiency are crucial when it comes to applications, and I'm generally excited about improving and extending existing methods while preserving their core concepts. And last, practicability and sustainable practices must be included when relevant to our tools. Often underappreciated, this direction is to me as important as the two others I listed earlier. So the integral joints you can see on the left are the result of ongoing work with Takeo Igarashi and Maria Parsa. And with that, thank you for your attention, and I'm happy to answer your questions now.
Okay, thank you very much for the great talk and also introducing many interesting the inverse problems for the architectures like locomotions and design as well. Like every slide has some like very beautiful the pictures and the videos. Really,
thank you. Yeah.
So the audience, if you have any questions, please post questions. Maybe I can start like with like asking some questions. Like some questions that I had for that the C-shell, the optimization was that you mentioned some kind of some constraint in the optimization the framework. Yeah, I thought that there might be some more interesting some constraints. Like obviously you might want to basically fix the position of like some nuts, or I guess there might be also some kind of a hard constraint in terms of like if the curvature of like some beams like becomes like exceeds some kind of threshold, then the beam might be broken. So those might also set some kind of some kind of the hard constraint for the curvature or something.
Absolutely, yeah. So, oh, sorry, yeah.
Yeah, so those are some kind of some thoughts that I had. Like I don't know. Like also you mentioned like the C cube, the idea at the end. Like so depending on how you basically like make some kind of joint to like those beams. Like the way that you're the bending those kind of beams might be different depending on the beams. So it may not be just like having some kind of some flat the beams attaching like this, but you might want to I don't know, so attaching some kind of beams like like orthogonal way. Then like this beam might be bending like this, and the other beam might be bending like this. Then those might be also making some more complex problems there. So I was wondering whether those might be also things that you're considering this.
Yeah, that's actually a great question. So we try to get as much as possible as hard constraints, but unfortunately, not everything can be easily incorporated. So you mentioned at the beginning that, for example, we can see it here with this example. Maybe we want the deployed joints to land on a circle or something like that. So that might be a hard constraint. And this is actually something we can add to the framework. That's something I haven't presented here, but this is as simple as just removing those variables from the optimization problem. These are really just pinning constraints, so they are easy to incorporate, and it's actually already there. We also mentioned different strategies. So in practice, I don't know if you see my camera, but in practice, I have this example. We won't have small motors, right, at the joint. So what we do is that we pull on the linkage. So that amounts to prescribing the position of some joints. So that's actually an actuation strategy that we also have, and we can also optimize to find the best way to manipulate these structures. So yes, these are constraints that are easily modeled, but you mentioned also like this fracture issue, which is actually very difficult to incorporate. So the proxy that we have is we use the elastic energy we minimize this elastic energy and hope that eventually we finish below the threshold, this von Mises stress criterion that we may think about. So unfortunately, we don't have a good way of prescribing a constraint here. So that if we do so, that would mean having the whole simulation as a constraint, which is quite heavy. So that's only softly enforced. You can tune the amount of regularization that you have on the elastic energy, which in turn decreases the stresses, but there is no guarantee here. For the tubes, sorry, I think I forgot exactly what you had in mind.
Some kind of, I don't know whether it really makes sense, but yeah, I thought some cases like you are somehow like making the joint of the beam like this. So like many of the examples they showed for the seashell case was like having the planar kind of the like some beam structures, like they are all bending in the same direction. But like what if we have some the beams like this, like one is like bending like this, and the other one is like bending in the like orthogonal way. So I don't know. So those might be also some like interesting way to somehow like connect those kind of the beams.
Yeah, it's a good point. Yeah, that's sorry. So let me put that back. It's a good point. So it's actually not so. Oops. Yeah, this is more a case by case thing. So I would imagine that maybe looking at the these bifurcations could be an interesting way of controlling this kind of multi-stable behavior. So I'm not sure I'm answering the question right here, but it's quite difficult to actually automatically control these like across many designs. They might have very different behaviors.
Yeah. Actually, the kind sort of the opposite things, the direction in terms of like making the problem might be easier. That I was thinking is that I thought that even there might be also interesting the applications, not just in the 3D, but also in the 2D as well. Like if we think about those kind of some line structure in the 2D. Like one thing that came to my mind was basically like, for example, like subway line map. Like Tokyo has like very complex the subway the line map. We want to make some kind of the very nice the subway the map with some kind of the lots of the constraints, with some kind of the length or some kind of bending for those kind of things. So I thought that these kind of the framework also could be applied to some 2D applications as well. So I was wondering whether you also explore those kind of directions.
Yeah, no, not really. I admit, no, not really. But that's yeah, yeah, definitely an interesting direction. Yeah, absolutely. No, we haven't.
I had some thoughts
Yeah,
like when you take
interesting.
the metro in many kind of big cities, like the map is super complex, and
Yeah,
the person who designed that kind of the survey map, the map might have some kind of the thought in terms of the some design the choices, right? With some kind of the regularizations, like in terms of that the interval uh, across the kind of the stations should be kind of uniform, or there should be kind of the like less amount of some kind of the bending in the lines. So those might be also
probably.
some kind of the 2D kind of examples for the things that you showed in here, right?
There is probably such a regularization. I don't know exactly. I mean, in our case, we want them to be as smooth as possible. I guess they want sometimes, like to have these very sharp turns. I don't know. Like that's some different regularization probably, but that's
Yeah.
quite
Yeah,
related.
so might be
That's
some kind of 2D.
interesting connection. I've never thought. Yeah.
One also the last question that I had was that so for some the cases that you show some the animation, those are my understanding is that as the regularization, you're basically applying some kind of the trying to minimize some kind of the dimension or something in the animation the case, right? So
Yes.
other than those kind of the regularizations, like one also the other direction that also people are doing these days would be basically having the regularization about some kind of the realism for each of the motions. So for those kind of cases, actually, we are also seeing many examples, so like somehow leveraging some pre-trained, some generated models, which is basically performing the role as the regularization to check whether the output is like realistic or not. So I thought that there might be also kind of the can be connected to your research as well. So
Absolutely.
have you also, yeah, for those kind of iterations.
Let me get the slide back with these cats. I guess that's what you're somewhat referring to. So here, we took a cat, but we could have taken like some human body. And of course, I would imagine that you can come up with ways to somewhat parameterize the space. Like, let's say you get a skeleton and you know that your elbow cannot cannot rotate more than some points. So you can maybe have these constraints on the joint angles. But in practice, as you said, it's not practical, and we have these now subspaces for human locomotion that we could actually leverage. And this is completely true, and this is actually something we can incorporate in our framework. So that's something we haven't tried yet. We just wanted to show like these inverse problem, but these inverse problems related to geometric locomotion in a broad sense. But in practice, that would be a very nice application, like plugging in SMPL or these kind of models to actually exactly enforce those semantic constraints. So that is, instead of having these soft objective term, as you can see here, that's actually so in the Stingray example that we show, if I can get it here, yes, let's play this. Yeah, in the Stingray example, we use vibrational modes. So it's just a change of variable, linear here, but that would be just replacing these modes with this map, learned map. Yeah, that's a very good point. Something we are actually interested in.
Yeah, that was very interesting to see.
Yeah.
Yes, I think there are lots of some interesting some future directions. So thank you for introducing the lots of the interesting work.
Sure.
Yeah.
My pleasure.
If we don't have any more questions from the audience, yeah, thank you, Quentin, and also Shin Young, for giving the wonderful talks today. I guess we can end the session here. Thank you very much again.
Thank you.
See you. Yeah. See you.